Okay, so hi everyone, so welcome to the second part of the tutorial about detecting doors from the bitmap floor plans. So in this part of the tutorial we will go through the basics of the faster RCN network, and then we will train the network in the Google Colab and see how's the performance. Okay, so let's quickly look what is the basic idea behind the faster RCN network. So the idea is that in practice we will fill the whole image with trial boxes of different sizes and shapes. So in this image, these red boxes, they correspond to the kind of negative samples, and then the magenta boxes are the positive samples, and then these green dashed boxes are the ground truth. So the reason why there's only not the whole image is filled is simply that I have only shown the 500 of the negative samples. So what are we going to do with the boxes is that from the boxes we're going to learn that if there's any kind of object at all, and further what kind of object it is. And maybe more interestingly, we're going to learn how should we transform the positive box so that it will match as well as possible the ground truth. So you could imagine that it's not likely that the original trial box will never exactly overlap the ground truth. And for that reason, what we're going to do in the network is that we will manually calculate the offset between the ground truth box and the positive box. And then we will calculate the difference between the prediction and the true one and use that as the loss function to learn the network. So one of the key features in faster RCN network is that there's actually two different kind of networks. So the first network is called the return proposal network, and it will simply give a rough estimate whether a box corresponds to any kind of object at all and what is the shape of it. And then there's a second network which will operate on the kind of positive samples from the first network, and then further refine what kind of object it actually is and what are the actual shape of it. So here's an example about the outcome of the first network. So we can see that it pretty nicely put the boxes in the correct places, but you can see that there's a huge amount of false positives, and you can see that the bounding boxes are not very well aligned. And then we can look what is the result of the second network, and it is shown in here. So here you can see that now there's much less false positives, and also the door bounding boxes are much better aligned with the real doors. However, you can also see that there's still quite many false positives from this run of the network. Okay, so that's kind of the rough description of the network. And maybe one thing to future mention is that when we say that we fill the image with the boxes, so what we're actually going to do is that we will run the image through this backbone, which is often this ResNet 15 or something like that. And actually we will then operate on this feature map, so we will not directly operate on the original input image, but instead we will operate on this feature map from this backbone network. But let's next step through the debugger quickly and see how are these parts actually implemented in the network. Okay, so let's quickly look what happens in the network during the training. So in the beginning we will simply create our faster RCN model. So maybe what's interesting here is that you can see that we're going to specify the sizes parameter and ratios parameter. So the sizes, they are simply the kind of the size of the bounding box, and then the ratios, it's the ratio between the width and height. So you can see that there's 5 different sizes and 5 different ratios. So that means that there will be in total of 5 times 5 boxes drawn at each position in the feature map. So that's quite the many. And then we will simply define our optimizer, which is going to be the Atom optimizer. And maybe worth mentioning is that we're going to use the learning rate scheduler. So in this case we will halve the learning rate after every 50 epochs. And then we're going to enter the actual training loop, so we will loop over the epochs, number of epochs, and inside each epoch we're going to loop over the images and targets in the data loader. And then we will call our loss, our model calculate the loss for each batch. Okay, let's then shortly loop what happens inside the forward method. So we are first calling our backbone, which in this case is simply the recent 15 network, to generate the feature map. If you look at the shape of the feature map, we can see that there's 2048 channels, each having a feature map of size 32 times 32, which makes sense because the original input image size was 1024, and for the last layer of the recent 15 the scale is 1 divided by 32, resulting into this 32 times 32 feature map. In the next step we are calling our region proposal network, and if we step inside the network we can see that it's quite a simple one. So it's generating two outputs, logits and offsets, and if we again look at the shape of the output, we can see that the shape of the logits, it's 25 times 32 times 32, which makes sense because there were 25 bounding boxes altogether, and those bounding boxes are positioned at each location in the feature map. And for the offsets, we can see that the shape is 100 times 32 times 32, which again makes sense because we have now 4 times more parameters. And that is because for each bounding box we need 4 parameters, the translation x, translation y, delta width and delta height, determining each offset for box. Okay, and then we enter the training specific parts. I'm not stepping inside each individual function here to save some time, but shortly describe what happens. In the first step, in the calc offsets batch, we are essentially placing the 25 anchor boxes at every location in the feature map. Then we calculate the overlap of the placed anchors by calculating the intersection of union score, and based on that score we divide the anchor boxes into negative and positive sample. This step is essentially visualized here. So the red boxes corresponds to low intersection of union score, for example below 0.2, and the magenta boxes corresponds to high intersection of union score, for example above 0.6. The negative samples, the negative indices, are only used to calculate the classification loss for the region proposal, meaning whether there's any kind of object or not. But then the positive indices and the true offset there are used to calculate the offset loss. And then we simply calculate the loss for the region proposal network based on the negative and positive samples and the true offset. The first part of the loss, the RP and CLS loss, is simply the binary loss entropy with logits, and the second part is the offset loop, which is essentially the smooth L1 loss. So that was essentially the first region proposal network. Okay, and then we start the second network. In the second part, we start by decoding the proposals, meaning that we apply the predicted offsets to the candidate proposals. The important part is that for each decoded proposal is that we call the detach function to stop propagation in graphs. This is because otherwise the two networks will be connected and the training will affect each other. Then we essentially repeat the step of determining the positive and negative samples and the true offsets in the select training samples methods. The key difference in the second network compared to the region proposal network is that we now feed the proposals to the ROI head. The ROI head essentially takes a snapshot from the feature map grouped to the proposed bounding box and divides that into an output grid, which is then fed to fully connected layer followed by separate fully connected layers for logits and offsets. And then we finally calculate the loss for the region of interest network in the same manner as for the region proposal network. So that was essential the training for the faster RCN network. Okay, and then we're ready to start training in the Google Colab. So for the first step to get started the training in Colab is to move your project in your drive. It's good to remember it's good to only transfer the files you really need to make the copying the files faster to the working directory in Colab. For example, copying the virtual environment will take forever. So let's look about the Colab side then. Okay, and then let's go to the Colab. So it's accessing some existing notebooks here, so let's select the Run Training notebook. So before entering the Colab, I have already copied the Python project to my drive folder. So at the beginning it's now simply enough to mount my drive to Colab using this first cell here. So it might take some time and it will ask some credential etc. before completing. Okay, now we're mounted on the drive folder. So then in the next step, it's good to copy the data from the specific folder to the Colab to speed up some things. So let's do that next. So this step will take some time. So that's why it is important to keep the size of the project in the drive as small as possible to avoid all the non-necessary files. So let's wait for some time. Okay, and then we're ready to start the training. So we can directly jump here to start our training. So the nice thing about Google Colab is that you get some limited amount of credits for free. So you can you have access to these Tesla T4 GPUs, which are quite decent, but I will now use the G4 machine, which is a bit faster, or quite a lot faster. And let's run it around 200 epochs at the first begin. And for this one, it's good to remember that we're kind of using this naive data loading, where the size of the images were predetermined and it's always cropped to the same place. So let's see what we get from this. Oh, sorry, what I remembered, so no, we're not in the correct folder, so let's simply run this step. So we need to enter the correct folder, so let's see if we are now able to run something. At least it looks a bit better. And starting. Okay, the problem here is that yeah, I was using the continue training parameter, so it was trying to continue from the previous one, but we don't have anything here, so let's do that since, and let's run once more and see if we proceed this time. Okay, and now we can see that we started doing something, getting some output logs, and it's going quite fast. So we're printing some basic metrics after each epoch, and to showing some precision and recall and stuff like that. And we are also writing those numbers to using summary writer to log files that we can then visualize using the tensor board. But anyway, this will take some time, so let's wait for a while, and then let's get back when the training is done, around after, let's say, 20 minutes or something. Okay, and then we finally completed our training after 200 epochs. So let's quickly look about the metrics numbers. So here you can see that there's actually multiple precisions and recalls corresponding to different threshold. So the idea here is that for each kind of detection we get a confidence score, and the smaller and based on that confidence score we can determine whether we accept the detection or not. So the smaller the threshold is, the more detections we get, but in practice the precision gets lower, so that's what's happening here. But anyway, we can see that for the most reasonable 0.5 threshold we see that that the precision is around 0.6 and the recall is only around 0.29. I'm a bit worried that why for the low threshold cases the recall is still so bad, but maybe there's something, some explanation there. But anyway, we can see that we did not get a very good result. I'm not that surprised because the training dataset was such a small and it was such a trivially handled. But anyway, let's copy the outputs to the summaries to the drive, and so that we can look them on the tensor board to see what's going on during the training. And let's also copy the output from the last epoch for the region proposals and the final detections to see something more. But anyway, let's next look about the tensor board. Okay, so let's launch the tensor board. So the tensor board, it actually comes readily within the Torch or the Torch Vision installation, and you can find it from the virtual environment bin directory. So we simply need to pass the log dir where we copied the summary files. So let's do that. And then simply launch it. And then we can navigate to the browser. And here we can see the metrics that we have recorded. So let's first look the test average loss. So here we can pretty much see what's the problem. So in practice, there's the test loss is not actually kind of really not decreasing that much. So it is within few epochs, and it reaches a minimum. So this means that we simply have a kind of too little data, so that the network will perform well in the test data. Maybe the surprising part is that the precision and stuff like that, they're still progressing rather well. And if you look the recall part, so yeah, so there's some let's say clear improvement, but we can see that we could have stopped it pretty much within the 18 to 100 epochs. But yeah, one thing that we could still look is to how does the outcomes actually look. So I recorded during the training, I recorded the proposals and the final boxes at every 20th epoch. So let's look how the proposals look for the final epoch. So you can see that the proposals are actually pretty good. So they're in the correct places and offsets are not that bad. So I'm kind of surprised they're looking that good. Then let's look the final detection. So this is a bit messy image, but yeah, you can see it's not that bad. So it's going pretty much in the correct position. Maybe here you can see some problems that obviously these kind of non-vertical or horizontal doors are not detected. So that is a kind of a problem. But these clear doors are relatively well find out. But yeah, anyway, I guess that was about that. So yeah, let's the one thing that we could still try to do with this basic faster RCN is that we could try to do the data augmentation. So let's do that quickly and rerun the training and see what happens if we with that improvement. Okay, so let's quickly look about the data augmentation part. So in this case, we're now passing the self-def augment data as true. So in that case, we will simply apply some random scale and rotation, but maybe more importantly, we will crop randomly the target image size from the original image. So in this case, we kind of get multiple different views from the single image, which significantly kind of increases the coverage. Let's quickly run again the data loader so that we can see what actually is happening there. So you can see that now that okay, it's every time it's kind of cropped from a bit random place, and also you can see that there's the small rotation applied every now and then. But yeah, maybe that's enough for about the dataset. So let's move to again the Colab and let's simply run the training again and see what happens with this stuff. Okay, so now we're back in the Colab. So I have already copied the required files to drive and back to the Colab. So it should be enough to simply run the script. So let's see what happens this time. So let's hope we get a bit smoother start this time. Okay, so it seems the training is running okay. So let's again wait for some time and see what is the end result. Okay, and now we finished the training, and if we quickly look the end result, well, we can see that maybe there's not that much improvement. If I remember correctly, the results were pretty much similar when we did not have a data augmentation. But let's look again the plots in the tensor board, if it gives a bit more information. Okay, and let's again launch the tensor board to see what's happening there. Okay, so let's look the test average loss first. Okay, so now we can see that the test average loss is actually looking much more reasonable. So it starts high and then it's slowly gets towards zero. However, we can see that at some point it seems to be getting a bit stuck there. And in addition, if we look the precision curve, we can see that yeah, it kind of reaches some the 0.4 region pretty soon, and then it's kind of plateaued there. So even the loss now behaves much better. There's not that much improvement in the actual precision or recall metrics. Okay, we can see that the recall is actually rising pretty well all the time, so it's possible that during some more training could have helped there. But anyway, let's not yet give up. And one more thing that we can try here is that the door detection is a bit tricky for faster RNA, and in the sense that the door area of the door is mostly like blank area. So and in also the door the door semantics, they are pretty small, so it's possible that if we only take the last layer of the ResNet, the feature map kind of loses all the information about the door. So in this case, it might be advantageous to use this called feature pyramid version of the faster RCNN, in which case we use all layers from the ResNet and kind of combine the information. So let's try that one more time, but let's do it in the final part of the tutorial. So let's see you next time, and let's see if we get anything, if we may improve from the position yet. Okay, so see you.